So in this segment, we address performance of a model in the context of classification. So as a refresher, classification is the context in which statistical variables are considered categorical. So we are interested in classes or categories or groups and how data points fall under one class or one group or one category versus another. Specifically, what we see illustrated here are data points illustrated with either squares or circles. But very importantly, I'm trying to highlight here in a specific color, in yellow, this is a boundary or frontier. So that is exactly what comes out the algorithms. When we train algorithms and there is an outcome from an algorithm, the so-called model, the prediction is precisely that frontier. So the analogy with this barrier, not barrier, but this boundary or frontier is the analogy is with the previous case in which we had data points and it was a regression problem, and the best fit regression line was the model prediction. That was the line that we considered the output of the model, and that line was used to make predictions. In this case, there is something that is more like a set of lines. This frontier or this boundary is composed or made of different pieces. But here, once the model outputs, that's what's the calculation, the outcome of calculation or calculations from a model. Once this boundary exists, then the predictions are to how the data points fall on one side of the boundary versus another side. And if they fall on one side, in this case, the side that is to the left, looking at this diagram here. So what's to the left of that boundary, that's going to be considered the prediction for one class, and then the class here, you can translate the classes. There are only two classes. This is a binary scenario, so you can translate the classes into integer values. Specifically here, there is the value of 0 and the value of 1. If it falls on the other side, then it's going to be a prediction. The data point is predicted as being classified with a class associated with the number 1. So here there are the color codes, squares, solid squares in black, and there are empty circles. Solid squares in black denote what's encoded with a value, integer value of 1. That is denoting one group or one class called fiction, and then empty circles or 0, the encoding of 0 is denoting the other group or class called nonfiction. So for classification models, the classification has to do with categorical variables. So the metric to quantify how well or how bad a classification model is performing, that which would be analogous to what we discussed for regression in terms of the sum of squares, or in terms of R square, some kind of metric that indicates this model is performing, with this much, how well suited the model is to describe the data. We need some type of measure here. So the way you measure this is, remember, these are for categories. So you would collect the categories. In this case, we're considering 2. You can also call them classes. You want to put this in a table, okay? And so this table is going to have one side over here, and it's going to have this other side on this other. So you could consider the rows and the columns. So the columns are going to keep track of what's predicted. The rows they're going to keep track of what is observed. Sometimes it's common to say that this is the actual observation, so observe or actual. You also keep track of the categories or the classes here. So I'm just saying cat for sure. And so this gives you a table. Actually, this table is the formal name for this is a matrix, and this matrix is keeping track of how the model may get things spot on, correct things, and how the model can be erroneous. So there is a word for this, there's a term here which has to do with confusion. Is the model confused? So this confusion matrix or confusion table would keep track of the misrepresentations. So basically, something is predicted. Let's say there's 0 and 1. So this is the encoding for the categories. And let's say here is 0 and here is 1. So this entry, row 1, column 1, represents scenarios where the prediction was 0 and what was observed was also 0. So that's a really good agreement. So on this entry, row 2, column 2, the prediction, so here you could say 0, 0, the pair maybe, and here the prediction was, something was predicted as 1, and it was also observed as 1. So that's kind of what you want to see. What you have on the off-diagonal entries of this table are things that were predicted to be one thing, but they would observe as the other thing. So those are the mistakes, those are the errors, those are the confusions of the model. But the things that are predicted as 0 and observed as 0, predicted as 1 and observed as 1, those things are spot on. And so those diagonal entries actually have names like true positive versus true negative. Here, don't worry too much about what's positive is negative. You can, just as we're saying that there is 2 integer values used to encode, they're just representing one category or one class. One is represented with 1, the other one is represented with a 0. The one that is represented with 1, we're going to consider that positive. And then the other one is going to be considered negative. So if something is predicted as 1 and is also observed as 1, that would be a scenario where something is predicted as positive, is observed as positive. That's a true positive. You could also call it true 1. And the other diagonal entry, something is predicted as 0 or negative and is observed as the same. That's a true negative. So the diagonal entries are called true ones, true zeros, true positives, true negatives. What's off the diagonal are scenarios where something is predicted and the opposite is observed. And then they have these names of false, either false negative or false positive. This positive negative is actually more applicable, for example, in a scenario where you're testing for somebody to have a disease, something like the flu or COVID-19, and so those tests would come back positive if the person actually has the disease, is testing positive for one disease, negative they don't. And those are scenarios in which you would prefer those true positives, predicted as having the disease and actually having it. That's kind of what you want. Disease in that context, predicting as not having the disease, that would be the negative, and actually not having it, that precisely those things. But some of those tests, they come with errors, and they may have false negatives and false positives. Now, these numbers represent from one model prediction, from one boundary, the data points are in one side of the boundary and another side of the boundary. So if you count the circles to the left, well, you count all the data points in the left, most of those data points are circles, which are predicted here as zeros, specifically as non-fiction. But there is one square there, right? So the square is representing a point that that's one of the errors. That would be one of the mistakes. So something that is predicted as a square, that would be predicted as 1, when in reality, I was referring to this square here, so it's actually predicted as a circle, predicted as 0, but is an actual, so that would be one scenario, predicted as 0, but is an actual 1. There is only one occurrence of such mistake or such error, and that's what you count. So if you count the number of predicted zeros that are actually circles, you would come up with the number of predicted zeros that are actually zeros. You count the circles here to the left of this boundary, and you would come up with this number, 18. Now, if you look at the squares to the right, those are predictions of the squares. The solid squares are representing the class encoded by 1. So those data points are predicted as 1, and they are in fact 1. So you would count 15 squares to the right of that boundary. And similarly, how many mistakes there are, data points that are predicted being on the right of the boundary means that the prediction is that that data point is a 1, but or it would be predicted as a square, when in fact is a circle. There are 3 of such occurrences. So the 1 and the 3 are denoting the mistakes or confusions of the moles, while the values of 15 and 18 are representing the instances in which the mole is spot on. So the metrics for evaluating performance of classification moles, there are multiple of these metrics or functions. One of them we're seeing here on the screen has the name accuracy. There is some called precision, F1 score, things like that. But accuracy, just for the sake of illustrating, if you plug in the values, you would evaluate this function according to what was the outcome of the mole. So you would use these values. So we evaluate or plug in, then we would get the numerator as with a value of 33. The denominator would add up to something like 37. You get a specific value. Okay. So of course these values are conditional on how the mole, what the mole is, and the mole is the boundaries. If the outcome is that there is a new boundary, everything is conditional on the data points. So let me just perhaps enforce, underscore that. So with a specific data set, the mole would produce the output. The outcome of the mole is a boundary, and then that boundary is what is used to classify the data points. So when you split the data into something called training data versus testing data versus validation, each of those training data is a subset of the original. The validation data is another subset. The testing data is another subset. For each of those subsets, there would be a boundary, there would be a mole prediction, and therefore there would be values for the confusion matrix.